Okay, we are going to get right into this, starting with classifying differential equations by their type. So, in order to do this, we can look at a couple criteria. First, what we're going to look at is whether or not they're ordinary, whether they're partial derivatives. So, in essence, for an ordinary derivative, you're going to have a function, say y of x. It need not be y of x, it could be f of x, f of t. Who cares? All we care about is that we're taking a derivative with respect to this variable in here. So dy dx could also be the second derivative. So this. And we can also multiply these derivatives by functions. We can even square them. We could take the square root of them. It doesn't really matter, just as long as the derivative is a total derivative and not a partial derivative, and we denote that with the d. So, obviously, then with a partial derivative, we're going to have functions of multiple variables, so that may be f of xy. A lot of times we use u of xt, or as you move into higher variables, you may have some arbitrary, just call it f of x1, x2, blah, blah, blah. And the partial derivative, we can actually denote this a few ways. One of them would be very similar to the derivative notation above, just we use this little del instead. So say we want to take the partial derivative of x with f with respect to x, we can do that. We can take the partial with respect to y, we can do that. We can also do the second with respect to x or y. And then something else we can do is we can take the first with respect to x and then the second with respect to y. Doesn't really matter. And then you can obviously extend this to as many variables as you like we have in the third example. Now, another way you can do it, which personally I prefer, is if I'm going to take this one. If you want to take the partial derivative of u with respect to x, I always just write u sub x. You can add in the xt. Doesn't, as long as it's specified somewhere, you don't really need to. Or you could take the derivative with respect to time. Additionally, you could do u with respect to x twice. So that's the second partial derivative. Second with respect to t. And then you can also mix it up and do x then t or t then x. You get the point. So now when we have a differential equation with these, we can really just look at, are there d's or are there del's? If there's d's, it's an ordinary differential equation. If there is a del, then it's obviously a partial differential equation. So I always look at the example, one of my favorite equations for partial differential equations. I just spent an entire month researching and writing I think it's the fourth chapter on, is the heat equation. So we have the partial derivative with respect to u equals this constant, we call it k, squared, and then the second partial derivative with respect to x. So on this side we have time derivatives, on this side we have spatial derivatives. So it is partial. Now if we have, say, dy dx equals 1 plus 2 square roots of x, doesn't matter what's over here, only care that this is a total derivative, so it's ordinary. We can also have sums of derivatives, or higher order derivatives, so you could have second with respect to x, plus 2y, it doesn't really matter what that function is, dy dx, again, total derivative equals who cares. And again, total derivative, total, this is ordinary. Good. So, moving right along, we can look at the order of a differential equation. So, this applies to both partial and ordinary. But in essence, the order is just the highest derivative. Now, we can look at the examples from before and Since the only derivative we have is a first order derivative, this would then be first order. This one, however, since we have a second derivative, we have second order. Now, don't be mistaken. A lot of beginners, not even necessarily in differential equations, but just calculus in general, like to assume that dy dx to some power, we'll call it n, is the same as the nth derivative with respect to x. This is not true. You can actually you could do an example to prove that. I mean, if we even take e to the x, derivative is just e to the x. Actually, the nth derivative is just e to the x. It doesn't matter. But on the right-hand side, we would have... Oh, that is the right-hand side, sorry. On the left-hand side, we have e to the x to the n, which these are not the same. So please do not make that mistake. So the next thing we can classify them using is linearity. Now, linearity means that we can write a differential equation in the form a sub n, which is a constant or a function of x only, and then the nth derivative of y plus a sub n minus 1, again, another function or constant, doesn't really matter, the n minus 1 derivative of y with respect to x, plus blah blah blah, all the way down to a sub 1 y prime, which is again another notation of writing an ordinary derivative, plus a sub 0 of just y equals some function g of x. Now, we can, I guess we can do an example where this is using variable coefficients. So as long as a sub n minus 1, yada yada, does not contain y in any capacity, and as long as these terms here are all linear, so we're not squaring them, we're not taking functions of them. So for example, 2x y double prime plus 9x to the fourth y prime minus 2 square roots of 3 y equals e to the negative 2x. Okay, so these do not depend on y, so that is great. These are all linear. They are not being composed. We're not raising them in any powers. Great. And then this is a function of x. Okay, so this is linear. Now, if we take, say, 2y y prime plus 2y cubed equals 4x squared. This is not linear. Why? Because, actually, there's two reasons. So first, we have y prime times this, which this depends on y, so automatically we know it's not going to be linear. Also, we have that y is being raised to the third power in the second term, so automatically we can tell this is nonlinear. Great, so this is where we really see two types of solution paths. For linear differential equations, you're going to be able to find an analytic or function with respect to x solution much more frequently. Now, I will say there are cases where you may not be able to find analytic solutions. You may have to approximate them numerically. However, that is going to be rarer than a nonlinear differential equation. The problem with them is they're very temperamental when it comes to their solutions. So a tiny change in x could cause a massive change in y because of this y cubed term, because of the multiplying y times y prime. You get the point. So oftentimes it is harder to find an analytic solution, and we actually do have to approximate most of them numerically. But with that being said, another way we can classify differential equations is homogeneity. So homogeneity simply means that all of the garbage on our left-hand side with the derivatives of y, with our functions of x, all of that equals 0. So we can force things into being homogeneous. However, not all differential equations are going to fall into this category, and there's specific techniques we can use to solve them whenever they do not play nicely. So, for example, if we have the nth order differential equation, we would have a sub n y n plus blah 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 a sub 0 y equals 0. Now, again, this is where don't be mistaken. Say we have some function a sub n, I don't know, let's say this equals f of x. What we can do is, I lied. F of x times one of the derivatives of y. So it doesn't really matter which one. We could have the nth derivative, we could have the first derivative, we could have no derivative. So we're just going to call it y. We can move this over and make this equal to 0. But if this is simply a term f of x, we cannot do that. And it would be non-homogeneous. Great. And the next thing we can do is look at, specifically for first order, you can do it for second order, but it's much rarer and it's easier to solve them using other techniques. But we can look to see if a differential equation is exact. So exact means that if we write it in a differential form, which what is the differential form? Instead of having dy dx equals some garbage, or dy dx plus some other term times y equals some garbage, instead we can take, I'll just do the examples. So if we have a function m of xy equals n of xy, that's a t, times dy dx, we can multiply by dx on both sides. So m xy equals n xy. Nope, I missed the dx in there. Apologies. And we can move that term over, and since it's kind of an arbitrary function, we'll just absorb the negative sign and call it m of xy dx plus n of xy dy equals 0. Great. So this is the first order case. Now, a differential equation is said to be exact if the following relation is true. So the partial derivative of m with respect to y equals the partial derivative of n with respect to x. So in that case, say we have m of xy equals, x squared y. And then on the right-hand side, we would have, or let's say we have n of xy equals, let's go with x cubed over 3 plus 2. Doesn't really matter about the constant part, but you get the point. So for this to be exact, I'll write out the differential equation. We'd have x squared y, that's our m of xy, dx plus the n of xy term, which was x cubed over 3 plus 2, dy equals 0. So test if this is exact. Take the derivative of this with respect to y. We would just get x squared. Take the derivative of that with respect, I meant to put a y. No, sorry. We are good. Okay. Take the derivative with respect to x of this we get, bring the power down, 3 divided by 3 is x squared, plus the constant is 0. So, since those are true, this is exact. Now, you can force a differential equation into being exact. In certain cases, doesn't always work, which we will talk about more in the next chapter on first-order techniques. So the next type of classification would be autonomous. Now, this is probably the most niche and least useful. Essentially, if a differential equation is autonomous, it means that the independent variable, that could be x, t, whatever, does not appear in the differential equation itself. So the differential equation doesn't depend on the independent variable. So for example, 2 times y double prime minus 3y prime plus 1 equals 0 is autonomous because x does not appear in any of these terms. Doesn't appear over here, doesn't appear here. You get the point. So, again, you could force something to be autonomous if you have, like, a bunch of x terms. You could divide by x and just say, don't let x equal 0. Cool. Again, this doesn't really... Autonomous doesn't make a difference, really, whenever it comes to solving these things. It more matters on linearity, homogeneity, obviously ordinary versus partial. So next, we are going to move into verifying solutions. So in the later chapters, once you solve one of the differential equations, whether that be one of the examples we do together, or whether that be one that you do in the exercises, it is always good to verify that what you have at least satisfies the differential equation. So, for example, we have the differential equation y double prime equals negative y. So, we are given the solution y equals sine of x. Okay, so what we want to do basically is take the second derivative of this function, which first derivative is cosine x, second derivative is negative sine x, and then we can plug these two into the differential equation to get that negative sine x equals negative sine x. Since this is true, y equals sine x is a solution. Great. We can do another example where we would have, say, c e to the cosine x. So take the this is going to be as a solution to y sine of x. Okay, I missed that step, and I'm like, that's not gonna fit into the one up here. So taking the first derivative, chain rule, c e to the cosine x times the derivative of cosine x is negative sine x. Okay. Equals what? Y times sine of x, which we had c e to cosine x sine x. So we are going to have apologies for the sine x term in there. So now see how there's a negative sign on this side, not a negative sign on that side. So these do not match up. But now if you tried, say, y equals c e to the negative cosine x times sine of, e to the negative cosine x, taking the derivative, Yep. These would verify. So again, we use this arbitrary constant, c. Now, we could have used any value of c we want. We could have used, I guess you could have trivially used 0. You could have used 1. You could have used 10. You could have used pi over 3. You could have used e to the square root of 2. It doesn't really matter what the number is, which is actually kind of a segue into the next section. But first, I'm going to give you another example where the solution does not match. So if we try y equals the square root of x to the solution, as a solution for differential equation y prime minus 3 equals 2x. Over here we have y prime equals 1 over 2 roots of x. Plugging that in, evidently, these are nowhere near the same. So, not a solution. Now, we are going to move into general and particular solutions. So, we saw in this example, we had the c. Now, we didn't specify what that c is, but we can, given certain conditions. So the general solution is always going to contain these random constants. So suppose we have the differential equation y prime equals 2x. So what is this saying? That the derivative of some function y is 2x. Well, we know that the derivative of x squared is simply 2x. But also, you can see that the derivative of x squared plus 1 is 2x. X squared plus e, x squared minus 1. It doesn't matter what this constant is. It's always going to go to 2x when we take the derivative of it. So we combine these into one constant, c. So we would write the general solution as x squared plus c. Now, instead, if we wanted to find a specific particular solution passing through a point, we would have to be given at least one condition. So the amount of initial or bound conditions you would need are going to depend on how many derivatives you have. So if you have 3 derivatives, you're going to need 3 conditions to be able to eliminate all 3 of the general constants you would get. So for example, if we have the case where the solution is y equals c e to the x, and we need it to pass through the point y of 0 equals 1. Great. We can take this 1, plug it in for y, equals c e, plug in 0 for the x. So we just have c equals 1, and we get y equals e to the x. Now, if suppose we wanted the condition y of 1 equals 2, again, plug in 2 for y equals c times e to the 1. So we would have c equals 2 over e. And then our solution is y equals 2 over e to the x. Or, if you want to write it nicer, 2e to the x minus 1. Great. Moving right along into solutions being linear. So what does this mean? If we have a solution y1 that satisfies a differential equation, if we have a solution y2 that satisfies the same differential equation, if we have y3, y4, and so on to yn, then the sum of all of these solutions, so y1 plus y2 plus y3 plus you get the point, is also a solution to that same differential equation. So we're going to go back to the example with y double prime equals negative y. So both solutions you can show y equals sine x, which we did, and then also y equals cosine x are valid solutions to this differential equation. So by linearity, the solution y equals sine of x plus cosine of x should equal, or should be a solution, apologies, to this same differential equation. So we can show that y prime equals cosine x minus sine x, y double prime equals negative sine x minus cosine x. So plugging these in, we have negative sine x minus cosine x equals the negative of y, which is negative sine x minus cosine x. Great, these match. So solutions are going to be linear, and this is something we're going to talk about more in partial differential equations when we get there. Still working on it. Right now I'm about 110 pages in, which I looked at the contents and what I want to put in there, and it makes me feel like my 110 pages is worth nothing. So, something else we can do is draw a slope field. Now, this actually is probably as simple as it sounds. So what we want to do is draw the Cartesian plane. And, wow, that is an awful line. And we are going to take points and then plug those xy coordinates into dy dx and get out a slope, which is going to be some number. Great. We are going to do the following example. dy dx equals x minus y. So once we plug in points, we're going to start with some easy ones. We're going to do 0, 0. We would get dy dx equals 0 minus 0, slope of 0. Great. Now let's plug in 1, 0. Plugging that in, we would get 1 minus 0, which is just 1. If we want to take the point 2, 0, we would get the slope 2. Then if we wanted to take the point 0, 1, we'd have 0 minus 1, so negative 1, 0, 2, gives us negative 2. Great. And also, you can see where x equals y, so the point 1, 1, we would have a slope of 0, 2, 2, 0, blah, 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 blah. So we can use a slope field to approximate what the solution would look like. Now what we do is we're going to draw little lines. Now they're not going to be super long, like just little tick marks with different slopes corresponding to these values. So 0 is just going to be a horizontal line. This 1 is going to be like a 45. The 2 is going to be steeper. Negative 1 is going to be this way. Negative 2 is going to be also pointing down, but a little steeper. So we can draw the slope field, which I'm just going to draw for these points I have here. So at 0, 0, we have a slope. I'm going to do it in a different color. Slope of 0. At 1, 0, we have a slope of 1, 2. Ah, crap. Sorry. Okay, that's supposed to be steeper than the 1. At 0, 1, we're going to have a negative 1. Negative, and then along this x line here, we're going to have horizontal lines. So in the end, our solution would trace out, depending on an initial condition, it's going to sketch out a curve that kind of looks like this. And stretches on to infinity in both directions. And in another section, and I believe the next chapter, we're going to solve that. We're going to solve that for this solution, y of x. So now we will be moving on after this to the wonderful world of solving first-order differential equations, which is where you really get to take the step into more conceptual, which we saw here, into some heavier math. Now, I would say this section, upcoming chapter 3, is going to be lighter than the rest, with the exception of maybe one. But this book is really meant to give an overview into differential equations. It wasn't meant to be a college-level textbook. It wasn't meant to be necessarily rigorous. Now, it's obviously meant to teach one something. I enjoy writing because it honestly helps me learn better and helps me commit more things to memory. Now, whenever I started the writing process, I took notes. I posted on my TikTok the notebook I had of the original table of contents. But I feel like whenever in my writing process, I learned so much more about the subject that you can't really get elsewhere. I feel like I learned best by teaching. Not to say I wasn't experienced in the subject before I dove into it and wrote about it, but I believe that doing so helped me solidify my understanding, if that makes sense. With that being said, that's going to wrap up the first lecture of what is going to be a series on this book, and maybe if I get around to it, I'll do it for the partial differential equations once it's done. Once I get around to it, I might do it for the integrals, or sums, or on rates of change. I don't know. There's a lot of things going on in my world, so I'm just flying by the seat of my pants. So, with that being said, thank you for watching, and I will see you next time.